Chapter 25, Statistical Thermodynamics, Section 25.1, Ensembles and Partition Functions. An ensemble is a collection of replicas of a system. Each replica is a mental copy of the same system. The average properties of a very large number of replicas of the same system in an ensemble are equal to the time-averaged property of such a system. There are various types of ensembles. So first, let's look at the NVE, micro-canonical ensemble. It's a collection of replicas of a system, and all those replicas have a fixed number of particles, volume, and energy. The NVE ensemble depicts an isolated system. NVT, canonical ensembles. They are collections of replicas of a system all having a fixed number of particles, volume, and now temperature. The NVT ensemble depicts a closed system immersed in an isothermal bath with a constant temperature. A mu-VT ground canonical ensemble is a collection of replicas of a system all having a constant chemical potential, volume, and temperature. The mu-VT ensemble depicts an open system at a constant temperature, constant volume that allows for matter exchange. A MPT Gibbs ensemble is a collection of replicas of a system all having a fixed number of particles, pressure, and temperature. The MPT ensemble depicts a closed system under constant pressure and temperature. Its volume may change. A NPH enthalpy ensemble is a collection of replicas of system, and all those replicas have a fixed number of particles, pressure, and enthalpy. The NPH ensemble depicts a closed system under constant pressure and enthalpy condition. Since we have constant pressure condition, Q is equal to delta H. And since H is constant, Q is equal to delta H, and Q is 0. An ensemble is a collection of replicas of a system, and those replicas are the mental copies of the same system. The NVE ensemble is a collection of replicas of a system all having a fixed number of particles, volume, and energy. The NVE ensemble is also called micro-canonical ensemble. The NVE micro-canonical ensemble represents an isolated system in which the energy is constant. Specifically, the internal energy is constant. Its entropy is maximized at equilibrium. Because we have this equation, du is TdS minus PdV plus the sum of mu I dNi. This equation comes from the definition of chemical potential mu. Now let's look at this equation. We have constant energy, and specifically constant internal energy. du is 0, dV is 0 because it's constant volume, and dNi is 0 because we have fixed number of particles for each type. So when we see this, that means the number of particles of each kind is constant. And then we have 0 equals TdS minus 0 plus 0, therefore ds is 0. That means, well, entropy is maximized at equilibrium in an isolated system, and that does make sense. Over here, this is just a simple diagram for a micro-canonical NVE ensemble over here with a perfect insulation. This shaded area represents a really good insulation. And we have a constant volume, and there's no work, no heat. The energy is constant. Also, we have a constant number of particles inside of each kind. This is again the NVE microcanonical ensemble. Now let's look at a different ensemble. A canonical ensemble is a collection of replicas of a system or having a fixed number of particles, volume, and temperature. The MVT canonical ensemble depicts a closed system. That means there's no matter exchange. It's immersed in an infinitely large thermal bath with a constant temperature T. Alright, so this diagram is a canonical MVT ensemble. Well, energy exchange is possible, so we can have heat flows in and out. Therefore, there is some energy oscillation in this kind of closed system. However, the number of particles, volume, and temperature are constant. In a canonical ensemble, Helmholtz energy is minimized at equilibrium because we have this equation for dA. dA is negative SdT minus PdV plus the sum of mu I dNi. This comes from the definition of mu. Because temperature is held constant, volume is constant, N sub I is constant, so dA must be 0. In this case, it must be minimized at equilibrium. Now let's look at the mu VT ground canonical ensemble. It's a collection of replicas of a system or having fixed temperature, volume, and chemical potential. So the mu VT ground canonical ensemble is an open system like this. There's matter exchange, there's energy exchange, but the temperature is constant. So you can imagine this is also immersed in a infinitely large thermal bath at a constant temperature, and also the volume is constant because we can simply just study all the chemicals inside this flask, and that means constant volume. However, there's matter exchange. Because dA is negative SdT minus PdV plus the sum mu I dNi, we can see temperature is constant, volume is constant, so dA is the sum of mu I dNi. Also, this constant chemical potential means for every single species mu is constant, and therefore this mu sub I is constant. We can put this mu I inside the differential. dA is simply the sum of the exact differential of Ni mu I. If you integrate both sides, you can see A is simply the sum of Ni mu I plus a constant. Now let's look at the NPT Gibbs ensemble. It's a collection of replicas of a system or having a fixed number of particles N. They have constant pressure P. They have the same temperature T. In this case, Gibbs energy is minimized because dG is negative SdT plus VdP plus the sum of mu I dNi. Again, this equation comes from the definition of mu. And now N is constant. Over here, this sum is 0. P is constant. VdP is 0. T is constant. Negative SdT is 0. Therefore, dG is 0. In NPT Gibbs ensemble, the Gibbs energy is minimized, therefore dG is 0. Most chemical reactions in a lab have a constant TP condition. The chemical reactions in an industrial process often also have constant TP condition. Constant T just for consistency, constant pressure for safety. You'd rather have a constant pressure than constant volume. When you have constant volume, well, gas pressure may accumulate inside this constant volume, which may cause explosion. So the NPT Gibbs ensemble depicts this kind of reactions on a constant temperature and pressure condition, and at equilibrium G is minimized. Over here we have Gibbs ensemble, or you can say it's NPT ensemble. We have constant N, constant P, and constant T. You can see there's a piston here now with a constant weight. So the pressure is going to be a constant, the number of particles is a constant, temperature is a constant. Just imagine we put this in a water bath or oil bath with a constant temperature. Finally, let's look at the MPH, enthalpy ensemble. It's a collection of replicas of a system, all having a fixed number of M, P, and H. Because we have constant pressure, that means the heat is isobaric heat, Q sub P. And in thermodynamics, we learned Q sub P is equal to delta H. Over here in this ensemble, H is held constant, so Q sub P is 0. There's no heat flow. In this case, entropy is maximized, because dH is TdS plus VdP plus the sum of mu I dI, and N is constant. This sum of mu I dI is 0, P is constant, VdP is 0, and H is constant, dH is 0, so ds must be 0. Entropy must be maximized. We can look at this diagram over here. This is a constant MPH ensemble, and you can see the pressure is constant. We have a piston here. The piston may move, the volume may change, but the pressure is constant. We do have an insulation over here. That is to ensure this Q sub P is just 0, therefore delta H is 0. So by having this really good insulation layer, delta H is 0. And in this case, the entropy of the system must be maximized. At the end, we have an equilibrium, and ds is 0. So we have briefly introduced 5 different statistical ensembles: micro-canonical NVE ensemble, canonical NVT ensemble, ground canonical mu-VT ensemble, Gibbs NPT ensemble, and this is enthalpy constant MPH ensemble. So in this chapter, we will only focus on 2 ensembles: the NVE micro-canonical ensemble and the MVT canonical ensemble. An ensemble is a collection of replicas or many copies of a system. In a canonical ensemble, all replicas have the same number of particles, they have the same volume, same temperature, but each replica may have a different energy. The number of replicas with energy E is proportional to this, e to the power negative E over kBT. This is the so-called Boltzmann distribution. We have learned before the Boltzmann distribution is associated with the most number of microstates, and this is the predominant configuration. The number of replicas with energy E is also proportional to the number of microstates such a system have. These two proportionalities result in most replicas having an energy very close to the average energy of all replicas. So if you look at this function, if we have higher energy, alright, this exponential function is smaller. But when you have a higher energy, well, the number of microstates of such a system with higher energy is larger. So these two mostly cancel. So in the end, we will see, well, the replicas with the energy that is really close to the average energy of all replicas has the most population. We will then look at one specific example. Let's examine one NVT ensemble that consists of only 25 particles. So all replicas contain 25 particles. Alright, and they have the constant volume and temperature condition. At the same temperature, all replicas in the NVT ensemble may have different energies. So that means energy oscillation is possible, but most replicas have energy very, very close to the average energy. We'll use an Excel sheet to calculate the relative population. That means the probability weighted or simple weight of the replicas versus their energy. For convenience, the energy of every replica is an integer multiple of epsilon. Well, epsilon is just kBT. So we'll just use this condition to simplify the calculation. When we have m energy quanta shared among m particles, there are this many microstates. We learned this from the chapter on probability and statistics. It's n plus n minus 1 factorial over n factorial over n minus 1 factorial. We'll prove this equation in this section. The probability of finding a replica with m energy quanta is proportional to this. The number of microstates, if you have this many energy, if you have this much energy, m times epsilon. And this is Boltzmann distribution, e to the power of negative m epsilon over kbt. So we're going to find this probability, all right? The product of the number of microstates and the Boltzmann distribution function are combined in here. And this is to allow us to estimate, the population of the replicas with, for example, 0 epsilon energy, 1 epsilon energy, 2 epsilon energy, 3 epsilon energy, etc. Now let's prove this equation. When m energy quanta are shared among m particles, there are this many microstates. There are m plus n minus 1 factorial over m factorial over n minus 1 factorial microstates. We'll prove this equation. We're going to just use a diagram here. We will illustrate this situation. M energy quanta being shared among m particles with sticks and circles. Each energy quantum is a stick. Each particle is a circle. Alright, now I'm drawing something like this. We have 8 circles. 1, 2, 3, 4, 5, 6, 7, 8. 8 circles. We have 11 sticks. Alright, so when I draw this, I'm trying to use this diagram to depict a situation in which 2 energy quanta are given to this molecule. 1 energy quantum given to this molecule. 2 energy quanta given to this molecule. 1 given to this molecule. 1 given to this molecule. 1 given to this molecule. 0 energy quanta given to this molecule. And finally 3 energy quanta given to this molecule. Alright, this is just a diagram of the distribution of the sticks to the circles. All the sticks are given to the immediate neighboring circles to their right. Alright, so these 2 are given to this, these 3 are given to this. So I'm going to use this kind of diagram. The rightmost item cannot be a stick. It has to be a circle. Because we need to give all those energy quanta to the particles. Alright, so if you have a stick at the end, that means this stick is not given to any particle. Alright, so that's not the scenario we analyze. We are analyzing all this m energy quanta shared among n particles. So this one is a little special. We have to have a circle at the end. We have an array of sticks and circles from left to right, but the rightmost item must be a circle or a particle to accept energy quanta. So this is fixed. Now you probably can see why we have n minus 1 in the end, n minus 1 over here, because we need to put 1 particle at the end. Alright, and then we will actually look at the permutations of the remaining items. We have 11 sticks and we have 8 minus 1 circles. Alright, 11 sticks and 7 circles. We have a total of 18 items right before the last circle. 18 items. The number of permutations of 18 items is 18 factorial. So now we have this on top, 18 factorial on top. The number of sticks, 11, plus number of circles, 8 minus 1, because we need 1 at the end. We cannot change that fact, so we have 18 factorial on top. And then we divide this 18 factorial by 11 factorial. Because among this 11 energy quanta, we can do permutations. You'll get the same scenario. So 18 factorial over 11 factorial. Now let's look at this 7 open circles. We can also do permutations of this 7 circles, and that's not going to change our diagram. For example, if I swap the first one and the third one, I swap these two circles. Does that make any difference? No. Yes, if I swap these two circles or these two circles or these two circles, any different? No. So we're going to divide 18 factorial by 11 factorial and divide it by 7 factorial. Now we have this equation. Alright, and for this specific case, when we assign 11 energy quanta to 8 molecules or 8 atoms, there are this many different ways, 31,824 ways to do that. We can easily numerically verify this equation with simple examples. If we give 3 energy quanta to 3 molecules, we plug in 3 here, 3 here. Alright, we have 5 factorial over 3 factorial over 2 factorial, we get 10 microstates. It's indeed 10. I mean, we can even count this 10 really easily. When you give 3 energy quanta to 3 molecules, we can have 300, right? We can have 210, 201, 120, 102, 012, 021, right? And also we can have 111. And I forgot to mention, you know, when I said 300, we can also have 030 and 003. So a total of 9 microstates. What if we have 4 energy quanta distributed among 3 molecules? Alright, we have 15 microstates. You just plug in 4 here, 3 here, 4 here, 3 here. And you get 6 factorial over 4 factorial over 2 factorial, it's 15. And we can quickly count this 15 microstates among 3 molecules. So we can have 400, 040, 004, right? And then we can have 310, 301, 130, 103, 031, and 013. And then we can have like 220, 202, 022, right? And then we can have 211, 121, 112. So if you sum up everything, you get 15 microstates. And now here's the numerical example. What if we have a canonical ensemble? Alright, let's say we have 25 particles, and I'm going to plot the relative population for different ensembles with this many energy quanta. Again, canonical ensemble means NVT are constant. The number of particles is 25, the volume is constant, and the temperature is constant. However, we can have energy oscillation. Alright, so that's why I'm putting a range here. The energy can be from 0 to 50. Again, the energy can be from 0 to 50. It's just the I can only put 16 of them here. We can compute the number of microstates. If you have 25 particles sharing 0 energy quantum, and we just have 1 microstate. What if you have 1 energy quantum? Well, we can give this one to any one of this 25 particles. Therefore, we have 25 microstates. Now, what if you have 2 energy quanta? Now it's kind of complicated. I will just use this equation. I'm going to use the factorial of 2 plus 25 minus 1 factorial on top. And then 2 factorial on the bottom, also 25 minus 1 factorial on the bottom. Alright, and then we get 325. Okay. And after that, we have 3 energy quanta, 2000 something. It's a little hard to calculate, but really the formula is easy. You have 3 plus 25 minus 1 factorial divided by 3 factorial divided by 25 minus 1 factorial. So over here I have the equation that I used in this spreadsheet. When we keep going, you can see the number of microstates going up. The more energy you have, the more ways you can distribute those energy to 25 particles. And now we need to look at the Boltzmann distribution. So in this case, when energy goes up, the Boltzmann distribution, you can see the exponential function goes down from 1 to 1.1 times 10 to the power of negative 7. So really small. How do we do this? It's pretty simple. We're assuming like KBT is just 1 epsilon. So over here it's e to the power of -0, e to the power of -1, e to the power of -2, e to the power of -3. Over here, this is e to the power of -16. Now let's look at the weight over here. How do we get this the weight over here? It's pretty simple. We'll just do this. We'll just do this, multiply by this. We get this number 125 times 0.368. I got 9.2. 325 times 0.135. We get 4.4. So this weight is simply the product of the number of microstates associated with some energy, and the Boltzmann exponential function associated with the same energy. Alright, now let's look at this. When we multiply this, I don't know, this one is roughly 6 times 10 to the power of 10, and this is 1 times 10 to the power of -7, so the product is this. Alright, and now what we can do is we can examine all those weight. The weight goes up, you can see the number goes up. Just look at the order, it goes up, right? But now let's look at the number more carefully. When does it reach maximum? I think somewhere here. Alright, between this n equals the quanta equals 13 and 14. We have the maximum. Alright, we have the maximum here, over here, around here. It's about 8,000. The weight reaches maximum, and then it drops to 7.7, 7.1. And again, just because I cannot put all 50 rows on this slide, so there are 34 more rows. So in the end, you can see the weight goes up. Over here we have 13 and 14 over here, and then it goes down. Eventually, when it reaches 250, the weight is going to be really small. When you have 50 energy quanta, again, the number of microstates is going to be huge, but this exponential function is going to be really small. Just imagine what is e to the power of -50. E to the power of -50 is a really small number. I think it's roughly 10 to the power of -22. So that's why the weight goes up first and then goes down. Alright, you have this kind of curve. You have a maximum. The peak is around 13 or 14. So you can see these two weights are the maximum. Now let's do weight times E. So we're going to calculate the average energy over here. So this is weight times E. We get all those numbers. And then weight averaged E. So that means we need to sum up all those numbers and then divide it by the sum of the weight. I got 14.55 epsilon. Alright, so all those ensembles, we can see different energy in different ensembles between 0 and 50. Alright, actually it can be 51, 52. It's just after this it's going to be negligible. Alright, so I only calculated it from 0 to 50 energy quanta. The weight reaches the maximum around 13 or 14, and the weight average energy in epsilon is 14.6. So what I did is I did the sum of this row or this column of weight times energy divided by the sum of this column of weight, and I get the weight averaged energy. And you can see the maximum is really close. 13, 14 is really close to 14.5. Again, this is just a numerical example. If you have 25 particles, assuming they can have different energy from 0 epsilon to 50 epsilon, you have this distribution. You have the weight here. The maximum weight is around here between 13 and 14. The average energy is 14.55 epsilon. So this here between 13 and 14, let's say 13.5-ish, is very close to 14.5 for this 25 particle system. Now let's increase the number of particles to 50. So what will happen is this. Now we have more particles. When there's no energy, there's only one microstate. When there's one energy quantum, there are 50 microstates, right? Because each of the 50 particles can get this energy quantum. When there are two energy quanta, that's more complicated. I will do just 2 plus 50 minus 1 factorial over 2 factorial over 50 minus 1 factorial, and get this number 1275. And I keep doing this for a total of 51 rows from 0 epsilon to 50 epsilon. And now this is Boltzmann exponential function. It's pretty simple. It's e to the power of negative energy over kBt. We were assuming h epsilon is kBt, and then this is e to the power of 0, e to the power of 1 over here. This is e to the power of negative 17, and we keep doing this. We get e to the power of negative 50, etc., etc. And we got this weight column. The weight column is the number of microstates times the Boltzmann exponential function, and we can just examine all those numbers. It just keeps going up until 17, because when you really look at this graph, it keeps going up until around 30. So at around 30, it reaches the maximum. All right, and the distribution is like this. Right. Now let's look at the average energy. We need to have the sum of this column of weight times energy divided by the sum of this column of weight. The average weight, the weight averaged energy in epsilon is 29. So 29 epsilon. Most replicas have an energy of 29 epsilon or close to it. All right, or very close to it. So I just want to emphasize this. When we have a MVT canonical ensemble, it's possible for the system to undergo energy exchange with its surroundings. That's why the energy of a MVT ensemble can have different energies, in this case from 0 to 100 epsilon. But really over here, you see the population or the weight or the probability of finding an ensemble reaches the maximum when its energy is really, really close to the average energy of all replicas. Now let's do some mathematical analysis. We define the partition function Q as follows. Alright, so we're going to just define this Q to be the sum of the Boltzmann exponential function. The Boltzmann distribution function is e to the power of negative energy over kBt. And we're define beta to be 1 over kBt. It's just for convenience. So Q is the sum of e to the power of negative beta epsilon I. Alright. If we have a 2-unit ensemble, that means we have only 2 replicas. We can prove this. Well, this uppercase Q, that is the canonical partition function of the entire ensemble. It's the product of the lowercase q sub a times the lowercase q sub b, which is q squared. The proof is as follows. So q sub a is for replica A, q sub b is for replica B. So qa times qb is this sum times this sum. When you do this sum times this sum, alright, you will be able to evaluate the product, which is just this. Alright, you can kind of verify this all by yourself. Over here you can see, let's say m is from 1 to 100, n is from 1 to 100. So you have 100 terms times 100 terms. Alright, and then you'll get 10,000 terms over here. Over here, m is from 1 to 100, n is from 1 to 100. So mathematically, we can just prove this is equal to this. All right. Again, if you really need a simpler example, it's just this. If we have a sum of 2 items and a sum of 2 items, we multiply this 2 sums, we get 4 items. Or you can say x1 plus y1, or x1 plus x2 times over here y1 plus y2, you get x1 times y1, you get x1 times y2, you get x2 times y1, you get x2 times y2. So that's a simpler mathematical example to convince you this equation holds. Now you can see this uppercase Q, which is the canonical partition function for the entire ensemble. It's just the product of the partition functions for every replica. There are 2 different scenarios. If you have distinguishable ensembles, the uppercase Q is simply Q to the power of n. But what if the ensembles are indistinguishable? Somehow we cannot view the n factorial permutations as n factorial different ensembles. And then that means we have to have this Q sub n, Q to the power of n, divided by n factorial as the number of permutations with n replica with the same scenario inside. Again, if you have n units, we can have n factorial different permutations. We're going to view this n factorial permutations as the same replica. Well, it's just counted as just one. Many particles, such as electrons, are indistinguishable. So eventually, when we count the number of microstates for those quantum particles, we'll keep this in mind. At certain stage, we need to divide the total number of microstates we counted divided by n factorial, where n is the number of particles. We'll have to do that. For molecules, there are 4 different types of partition functions, including 3 for nuclei and 1 for electrons. The 3 partition functions for the motions of nuclei are here: translation, rotation, and vibration of nuclei. You can also say they are translation, rotation, and vibration of molecules, because when we are looking at the translation, rotation, and vibration of molecules, mostly those are the motions of the nuclei. The electrons just move accordingly. Finally, we have a partition function for electrons. It's called electronic partition function. It includes the potential and the kinetic energy of electrons, and also, just by convention, when we say electronic energy, sometimes we are including the nucleus repulsion in this electronic energy. All right, it's just convention, or we just call that electronic energy. Now the partition function is multiplicative. So if you have molecule, you have translational partition function, rotational partition function, vibrational partition function, and electronic partition function. The product of this 4 will give you the total partition function of the molecule. The partition function of one replica in a canonical ensemble is therefore this. Now it's a little complicated. Q is the sum of e to the power of negative beta over times epsilon n. Epsilon n, well, it's the sum of the translational energy, rotational energy, vibrational energy, and electronic energy. And they can all have their own different energy levels. Like translational energy, you go from 0, 1, 2, 3, 4, 5. Oh, but wait. For translational energy, you cannot have a quantum number of 0. So you start with 1, and then 2, 3, 4, 5. Rotational energy levels, you can go from 0, 0, 1, 2, 3, 4, etc. Vibrational energy, well, it's 1/2 plus n times h nu, and that n can be 0, 1, 2, 3, 4. And then electronic energy, well, whatever molecule you have, we can have many electronic energy levels. So we get this sum, and then we can separate this sum into 4 parts, the product of 4 different sums. Alright, so we have translational partition function here, rotational partition function, vibrational partition function, and electronic partition function. Beta is just defined to be 1 over kBt for convenience. Now if we have a n-unit distinguishable ensemble, the uppercase Q is the lowercase q to the power of n. What if the ensembles are indistinguishable? Then we need to divide this whole thing by n factorial. Now let's derive the average energy of a particle in a many particle system at temperature T. Alright, we can calculate this if we know its partition function. The definition of the partition function is this: the lowercase q for this replica is the sum of the Boltzmann exponential function e to the power of negative beta times epsilon n. Beta is 1 over kBt, epsilon n is just the different energy levels. The probability of a particle occupying energy level k is this. It's this Boltzmann distribution function at energy level k, and over here those are the sum of all Boltzmann exponential functions at different energy levels. So we have the average energy, or weighted average energy, is this. It's the sum of the energy of each level multiplied by the probability of a particle in this level. So epsilon k is here, the probability is this. I'm gonna just plug in this probability over here, and then we get this expression. Okay, we get this expression. It's the sum of epsilon k times this fraction. In this fraction we have this on the bottom, and this thing on the bottom, this is simply q. Alright, this is simply q. And you can take q out of the sum because q is independent of the value of k here, so you can take the q out. Alright, and then after you take this q out, you have this expression, a sum of epsilon n times the Boltzmann exponential function e to the power of negative beta epsilon n, and then divided by q. K and n are so-called dummy indexes, so really that means if you replace this n with alpha, you get the same sum. Alright, here's an example. If you calculate the sum of I from 1 to 3, you get 6. If you calculate the sum of alpha from 1 to 3, you also get 6. It does not matter what the dummy index you use. Same here. I mean, if you sum it up, for n equals 1 to infinity, it's the same as summing up this for alpha from 1 to infinity. Alright. Now we got this equation, nice equation. The average energy is the sum of epsilon n times e to the power of negative beta epsilon n over q, and therefore q times the average energy is this sum. The sum of epsilon n times e to the power of negative beta epsilon n. So we get this equation. And somehow if we can evaluate q, and if we can evaluate this sum, we get the average energy. And we'll do that. It's pretty tricky. There's a mathematical trick about this. We want to get the sum of epsilon n times e to the power of negative beta epsilon n. How do we do that? Actually, we start with dq over d beta. So this is dq over d beta. Q is the sum of the Boltzmann exponential function. The derivative of a sum is the sum of the derivatives. So this is what I did from here to here. Alright, so if you're doing, for example, the derivative of x plus y, well, that's just the sum of the first derivative of x and the derivative of y. So this is true mathematically. And then we can evaluate this. It's really easy because we have exponential function over here, right? So we just copy this exponential function here and then use the chain rule. We should look at the derivative here, which is negative epsilon n. Also, from here to here, you probably realize why we define beta to be 1 over kBt. When you do this first derivative, it's really convenient. Alright, so it's just negative epsilon n from the exponential term multiplied by this exponential function. And remember, we did this only because in the previous page we see this expression is Q times the average energy. So this is just a negative Q times the average energy. Alright, so dq over d beta is just negative Q. This part is negative Q times the average energy. And therefore, the average energy is just negative dq over Q over d beta. And now dq over Q is d ln Q. Why is that? Because you can see d ln Q over dq is 1 over Q. Therefore, dq over Q is d ln Q. So the average energy is negative d ln Q over d beta. So that's a pretty simple expression over there. D beta, well, can be written as the differential of 1 over kBt because beta is defined to be the reciprocal of kBt. And when you do that, you can evaluate this divided by dt. Well, it's negative kBt squared, the reciprocal of this. So you can see the my derivation over here. I'm just taking the derivative of beta, or 1 over kBt over dt. I get negative 1 over kBt squared. Alright, so this is dt times negative 1 kBt squared. And then because negative 1 kBt squared is on the bottom, we flip that up, and because there's a negative sign here, and there's a second negative sign here for like division, they cancel. Now we have just a simpler expression for the average energy. Again, we have this equation from just calculus, and d beta is this, and d beta is simply negative 1 over kBt squared times dt. So we can replace this d beta with this. We can simplify everything. And now we have the expression for the average energy of the particle in an NVT, canonical ensemble. It's negative d ln Q over d beta. It's kBt squared d ln Q over dt. And also, we can express this as kBt times d ln Q over d ln T. It's just because d ln T over dt is 1 over T. Therefore, we can just kind of move one of the two t's here to the bottom. You get dt over t. dt over t is d ln T. So we got this expression as well. So if we have the expression of Q in terms of beta or T, we can plug in that expression of Q in terms of beta here. We can plug in the expression of Q in terms of T here or here. And then we simply take first derivatives, alright, 3 different derivatives. We will be able to get the average energy of the particle. So the first thing is to determine the expression of Q, the partition function, in terms of beta or T.